Hey guys, today we will solving the insane web challenge named ApexSurvive from Hack the Box Cyber Apocalypse CTF. We are solving it the intended way. The challenge gives us this pretty guideline, which explains the challenge scope and the email inbox the challenge provides us. Please take a moment and read it. Anyway, let's open the email inbox and the challenge a new tab. This is our pretty and cheap email inbox. We will use the email provided by challenge to register and login. We are redirected to the settings page and it says to verify our email. Anyway, let's try to access the home page. We have to first verify our email to access anything. Let's send verification link and reload the inbox. And we are verified. Let's see the home page. All right, let's dive into the inner workings of this marketplace platform. We'll start by dissecting its functionality and then take a peek behind the scenes into the source code. First off, let's explore what regular users can access. They can browse products and report any issues they encounter. Simple enough, right? Now, let's delve into the nitty-gritty details by examining the Docker file. It seems they're using an outdated version of Alpine version 14. Not the most up-to-date choice, but let's see how it pans out. The setup involves installing necessary packages and configuring the challenge with Mailhog as the SMTP server. However, the use of an older Alpine version may pose some security risks. Moving on to the entry point, we see it starts the MySQL server, sets up the database, and initiates the supervisor to manage processes. Examining the supervisor config, we find that the challenge process is managed by UWSG. Let's check the UWSG config file. It's configured to run with root privileges, employing 4 processes, and checks for file changes every 3 seconds. Now, on to the application itself. It's built with Flask, setting up the database, mail client, routes, and error handlers. Additionally, it includes a response header related to service workers. The database file contains standard functions for data retrieval and updating, seemingly secure against SQL injection. All right, in the routes, we discover some intriguing functionality, including a few routes inaccessible to regular users. Additionally, there are some decorator functions with names that are pretty self-explanatory for now. One notable route is the redirection of users based on a provided URL parameter. Looking at the API routes, it's apparent that they're quite similar to the routes we've already explored. In the login process, the application sets the cookie same-site attribute to strict, which is worth noting. Now let's investigate the middlewares to see if we can gain access to additional functionality. On top, we observe some allowed tags and allowed attributes. These must be utilized by the sanitize input decorator we encountered earlier in the API routes functionality. Authentication middleware ensures session cookie presence and verifies tokens. Further middleware checks for user verification status and admin privileges, while also protecting against CSRF attacks and sanitizing input. Since there is no way for us to bypass the middleware checks, let's take a closer look at the profile update functionality. So, essentially, if the update profile function returns an email change value, it triggers the send email function, passing the new email and user ID as parameters. Let's look at the update profile function. So if the email entered by the user is different from the value stored in the email column, or if it's an unconfirmed email, the function returns email changed and also sets the user to unverified status while generating a confirmation token. Check in the verify email function. If the host name in the email is equal to ApexSurvive.htb, then it sets the isInternal flag to true. All right, now let's examine the send email function defined in util.py. So this function retrieves the token from the database and then generates the email body using a render template string. Subsequently, it sends the email to the address passed as a parameter. This specific implementation looks fine initially, but this is vulnerable to race condition. What if we update the email and the delay between fetching the confirmation token, we update our email again to internal user, so it will send internal user confirmation to our email. We can quickly verify this bug using Burp Suite. Burp is up and running. First, we configure our browser to funnel every request straight into Burp Suite's watchful eye. We've got our browser primed to send every request through Burp for a closer look. After tweaking our profile, we hit save without hesitation. Over in Burp, we're diving deep into the request, taking a closer look in repeater mode. To exploit the race condition, we need to send the same request to repeater twice. Now, let's group all these requests together and set them to be sent in parallel. For the first request, let's configure it to act as an internal user, triggering the email change process since we're currently a verified user. Keep the second request unchanged. And for the last one, let's set the email back to internal again. This way, when the application processes the second request, which will be our email, the last one will change the confirmation token and set it to an internal user confirmed token. Now let's send the request. But it didn't work as expected. Let's delete all emails and try again. Let's run the attack twice. After a couple of tries, success. Persistence pays off. With access granted, we waste no time in exploring the internal settings. The product add functionality explicitly instructs the user to add HTML, indicating a potential for HTML injection. Can we escalate this to XSS? Let's investigate how the platform renders the products. The product descriptions are rendered with Jinja, which escapes HTML, but it uses DOM Purify to prevent XSS. However, DOM Purify under these settings allows the style element, making it vulnerable to CSS injection. But what can we do with CSS injection? Well, we can leak data from this page. Upon closer inspection, we can see there's an anti-CSRF token on the page. What if we leak it and perform CSRF? However, it's worth noting that the application is secure from CSRF as it uses a strict same-site cookie. Let's explore more. It was setting a service worker header, indicating some functionality. We should investigate the implementation of the service worker to better understand its role. So it registers the service worker and also passes a host and version parameter to the service worker script. Let's take a closer look at the service worker script to understand its functionality. The script fetches the host and version from URL parameters before importing the workbox script. Workbox serves to unify routing and strategy modules, enhancing caching and file serving capabilities. Initially, it configures image caching and sets the default handler. Towards the end, it establishes a specific routing strategy, including a timeout for profile updates to manage server load effectively. Upon inspecting the navbar, we notice it renders the username while ensuring HTML is not properly escaped, yet this leaves it vulnerable to HTML injection. While this implementation seems secure, it remains susceptible to service worker hijacking. In the event of HTML injection, if an attacker injects an element with the same ID, it will fetch the first matching element, which will be attacker-injected element. Additionally, prior to Chrome 97, service workers disregarded same-site cookie settings, leaving users vulnerable to CSRF attacks, even with cookies set to same-site strict. If service workers are being used by an application, let's verify the version of Chrome that the target is using to run the bot. Got it. Even though I used the wrong command, the Chroma driver version aligns with Chrome 93, making it vulnerable to CSRF. So we can execute CSS injection to leak the CSRF token, then proceed with CSRF to exploit service worker hijacking. Let's dive in and explore this further. I've downloaded Chrome before version 97. First, let's conduct a local test. We'll utilize specific settings to bypass SL certificate checks. For CSS injection, if you're not familiar, I recommend reading this blog from Portswigger. Additionally, we'll use a specific tool for conducting CSS injection. We need to update this tool a bit because the current payload uses the HTML has selector, which is not available in older Chrome versions. We're using this tool as a base so we don't have to start from scratch. We only need to exfiltrate the input element, so let's remove the text area form and anchor tag from the list. Now let's remove the characters we know don't exist in the token. Examining the token, it's alphanumeric, containing lowercase letters, numbers, and hyphens. Hence, in our Oracle, we don't need capital alphabet symbols or spaces. Now, we need to update the payload. We have to add a CSS property for every input box so that the display is set to block. This ensures that the browser executes the background property, enabling data exfiltration. Once that's done, we can remove the HTML hash selector from the payload and the parentheses as well. Furthermore, let's change HTML to input so that all the variables it generates are for input elements. Now let's proceed to test this on our account first. Let's initiate the Oracle and add a new item. Then let's include the CSS injection payload in the description. We're utilizing a paragraph element because if we directly pass a style element, DOM Purify will escape it. Therefore, we need to place the style element inside another element. The product has been added. Now let's visit it in our Chrome browser. It says exfiltrating, gonna speed up the video. Hold on tight, folks. And voila, we've obtained the token. Now, here's the snag whenever we report a product using the bot. It logs into the web app, causing the token to change each time. One good solution for this issue is to use WebSockets. Let's add that functionality in our code. But first, let's close the current server and install socket.io, a library used for WebSockets implementation. Now, we need to integrate WebSockets into this HTTP server. To do that, remove the following piece of code. Import server from socket.io. Initialize the WebSocket server. And whenever a user connects to the WebSockets, log it in the console. Afterward, start the HTTP server on the same port. All right, WebSockets are set up. Now let's move on to implementing the CSRF part. We'll define a root route and write down our payload in this HTML variable later. Now, let's return the HTML. We have to define a form with the method set to post and the action set to the profile endpoint. Next, we need to define all the parameters. Let's simply copy and paste the names. We don't have the value of the anti-CSRF token yet, so we'll keep it empty for now and set an ID so we can easily change its value once we obtain the token. Now, let's import the socket.io JavaScript so we can listen for data. Set up socket.io. Next, we need to listen for token events. Whenever there's an event named token, we'll set the data as the value for the anti-CSRF input and submit the form. Lastly, whenever a user visits the page, a new tab will open to the CSS injection payload page, triggering CSS injection in the new tab while our WebSockets work in the background. Now, the final step is to broadcast the token once we've obtained it. But before that, let's turn off this setting, which basically displays the result in the browser. Here, we will simply add a check. If the token length that we've already exfiltrated is equal to 36, since that's the length of all tokens, then we'll broadcast the token and log it in the terminal as well. Now we are ready to test it. Let's start our server and check the CSRF on our account. Fuck, I made a spelling error. Let's fix it. Ah, why am I so dumb? Let's patch it again. All right, now it should work. All right, it's working. Now, the title of the previous page has been changed and the page is fully loaded, meaning CSRF is executed. Nice. We have successfully exploited CSRF. And if we check the cookie, it's set to strict. See? Magic? Now we have to perform service worker hijacking. For that, we need to change the username to an anchor tag with the service worker host as its ID attribute. We're using anchor tags because the sanitize input on the backend only supports that specific element with an ID, and set the inner text to our server. So it uses our server to fetch this workbox, and we can execute malicious code in the service worker and hijack it. Now, let's define another route for the workbox script. Well, we could create a separate file and just serve it, but I'm going to do it this way because I'm a bit lazy and I want longer videos. So not going to explain. It's self-explanatory. We did this already. Change the content type from HTML to JavaScript. Now, if we want to successfully register our malicious service worker, we have to import the workbox script in our payload. Currently, the service worker is utilizing workbox. If it's not there, the script will error out, and the browser will not register our service worker. Now, in order to read the cookie, we can't use document.cookie. We have to use cookie store, and once we get the cookie, send it to our server. Now that it's done, we need to define another route that will simply log the data in the console. However, we have to set up cores for it. Again, you could do it in a different way, but as I said, I'm going to do it this way. Well, let's just suffer through it together. Set the headers to ensure proper acceptance of requests. If the request method is options, return a 204 status code along with the headers. Else just return OK and log the URL. Now we are good to go. Now, CSRF is done. If we simply visit any page, it should trigger the service worker hijacking. However, it didn't work, probably because any route defined after the root endpoint won't function properly. Let's move it up. If we reload, we get the cookie in our terminal. Now let's attack the admin and steal cookies. We will use ngrok, so we have to change all instances of localhost in our code. Now we have to add a new product with the ngrok URL and change the window.open to product number 8, since we already added one product while testing on the local account. And also change the email to the admin user email, because if we change the email as well with CSRF, it will make the account unverified, and then there is no point in stealing the cookie. Now it's done. We will use path traversal to perform an open redirect to our malicious site. And change the wait time settings because we are using ngrok. 200 milliseconds is a bit unrealistic, so let's set it to 2 seconds and restart the server. Let's fire up our attack. Let's report a normal product to trigger the service worker hijacking. Let's change our session to that of an admin. Now that we have access to the contract document settings, Let's close all this first. Now, let's understand the functionality of the contract route. All right, it's a basic one. It simply checks if the uploaded file is a PDF and then saves it in the contract directory. However, there is no sanitization, so it's possible to overwrite files using path traversal. If we check the check PDF function. So basically it uses a PDF reader. If the PDF reader is unable to open the file as a PDF, it errors out. So we can overwrite files on system with PDF. If we search for any remote code execution method involving overwriting PDF files. We found this blog post and it's essential to read it. In short, the UWSG configuration doesn't handle garbage data in its files properly. It parses the configuration regardless of any invalid or unexpected input. So if we embed a UWSG configuration setting within the metadata of a PDF file, the UWSG server will parse it. Since the application checks for changes every 3 seconds, we can leverage this behavior. Let's copy the exploit from the blog. Set the exfiltration server to our webhook. Execute the read flag command. Ensure proper indentation in the code. Now, we need to upload the modified PDF file and configure Burp Suite as a proxy to intercept the request so that we can change the file name before it reaches the server. First, we'll overwrite the UWSG config file with our modified PDF containing the malicious config settings in its metadata. Once the config is updated, then we'll change any of the Python files to trigger a forced server reload. This will cause the server to parse the malicious config and execute our commands. It's restarting the server now. This process might take 1 or 2 minutes to complete the reload, so I'll fast forward the video. It made the request, so we got the flag. Thanks for watching. Don't forget to subscribe, like, and comment anything you want me to make videos about. See you next time.